Today we're joined again with James Douma, a machine learning expert, a Tesla investor, and becoming a frequent guest on my channel. Welcome, James.
Great to be here.
Yeah, so this is episode or part 2 of my conversation. Just earlier, we talked about kind of an inside look into the architecture of Tesla's full self-driving software, but also how they're transitioning more and more into a bird's eye view. So they're fusioning their cameras together and kind of creating a view from the top and using that to help with controlling and directing the car. In this episode, we wanted to continue discussion on a February 2020 talk from Andrej Karpathy at Scaled ML, where he kind of laid out a lot of, this is probably the most recent talk of in depth with Tesla full self-driving architecture. Is that correct, James?
Yeah, I think that's, I mean, I'm sure that if he were to do it this month, there'd be all kinds of new great stuff to learn. But this is the most recent one where he actually talked in some useful amount of detail to a machine learning oriented audience about how they were doing things inside autopilot.
Cool. Yeah. So we're going to jump into what Tesla or Andrej Karpathy is calling pseudo-lidar, and how Tesla is able to figure out depth of field, how far things are from the car, and how that helps them in driving. But first, did you hear about, was it Elon recently, I think a couple of days ago, saying that the next update is going to be like a step change for full self-driving? I think they haven't had an update in like over 3 weeks or something with the full self-driving beta. Have you heard anything about that?
4 now, right?
Yeah, almost 4 weeks or so.
Yeah.
What do you think? Why do you think there's been this lag, and do you think something is happening where they are going to significantly improve it?
Well, I mean, the two possibilities spring to mind. One is they found they found a catching point. They found a problem that they really needed a better solution to. Another possibility is that they have this technique sitting in the wings that they've been polishing that they want to bring into the code base, and they haven't brought it in because it was too immature. And now it's to the point where they want to try to merge it. Whenever you make a structural change, you have to touch a lot of things. You have to make a bunch of code changes, and your labeling stack might have to change. It seemed like his tweet was sort of alluding that they to something along those lines. Like I had been concerned, like some of the people in the FSD beta program seemed like they hadn't been super impressed with the performance improvements that they were getting in the last couple of things. And then we got this big long pause, which I had been thinking maybe, they've found a stumbling block that they need to rethink. And so they're taking a break while they figure out this problem before they move on. But then the way that Elon was talking about it in his tweet, it kind of sounds more like the latter thing, where they have something new that they want to bring into it, and they can't do that smoothly. They need to take a break in order to be able to bring it in. Mm-hmm. So we'll see when it comes out. I don't know if I'll be lucky enough to the security's going up and up all the time. And so I don't know if I'll ever get to see a network again, but if I do, it'll be interesting to see what changed.
Have you ridden in a full self-driving beta vehicle yet?
Yeah, I did get a ride in one a couple months ago.
Okay. All right.
The 4th version, I think.
Okay. Awesome. So let's dive into this. I'm curious what we can learn. This is kind of like a personal learning session for me to dive into kind of the ins and outs of full self-driving beta. Actually, before we dive in, I had another question. What do you think about the timeline of full self-driving? Do you expect it, let's say 2021, how do you expect improvements to happen? Do you expect the next several months to be more slower, and then at a certain point, the improvements get better, or it reaches a point where it just becomes really good enough to do more of a wide release beta? And how long do you think that takes? Is it imminent, you think, kind of a full, a wide release beta, or do you think it's at least several months out?
Well, I think that they could do a wide release whenever they decide they want to. And the thing that I don't think that they're not doing wide release because they can't do it safely. I think if they wanted to, I think they're probably at a point right now where the upside to the company of doing it isn't doesn't outweigh the downside of the complexity of rolling it out and dealing with, the headaches associated with that. At some point, you really want a lot more people driving it. And when they get to that point, I think they can roll it out. I mean, there are a bunch of components of FSD that are clearly dramatically superior to AP today in terms of its awareness of the environment and that kind of stuff. I think they've been really focused on getting the city street function working. Right? And that they want to get to some level of functionality where they need to roll it out to a larger number of people before it makes sense to do that. And it's an interesting question. I don't really have a good answer to it.
Yeah, interesting. Let's dive into the scaled ML talk, if you don't mind. And I'd love to hear your thoughts on it.
Speaking generally on the topic of like rolling one of these functions out and when it's done, the progress, the technical progress that the tool itself can be making, frequently you can be making improvements by leaps and bounds, and the end user doesn't really see it because the end user needs it to cross a certain threshold before it adds, before a new use case appears that they can use. Voice recognition is an example of like voice recognition. Like 20 years ago, I was doing voice recognition for systems that were inside cars with these learn out in house bee things. And ever since then, voice recognition has gotten dramatically better. And yet it wasn't useful in cars for a really long time, right? It had to get to a recognition accuracy that would enable a simple enough user interface that people didn't have to be experts in order to use this thing in a car. So despite the fact that the technology itself has gotten better like 50% a year every year for 20 years or something, it's only very recently that it started crossing the threshold that people could use it. So my prediction about autopilot is that you're probably going to see the error rates, like, in the number, say, interventions, for lack of a better term, like how often do you have to intervene? Every time that goes down a factor of 2, that's a huge step forward in the accuracy of the system as a whole. But how many 2 times reductions do we have to have before your average user thinks it's done, it's good enough, and they can move forward, right? And that's actually, I think, harder to say than how fast the product is improving. Like, at what point is it good enough? That's pretty tough. And that's a theme kind of in the self-driving thing. I think Google a long time ago thought that they understood what was going to be good enough, and they were making their predictions about when they were going to be done based on that. And it just turned out that good enough was a much higher bar than they thought it was. Like, they knew how fast the tech was improving, and they thought they had an idea where they needed to get to. But then when they got there, they realized that in the real world, it still wasn't. So I would say that's actually the bigger uncertainty. It's not, how fast is the technology improving, but how good is good enough? I think that's a kind of thing that you got to drive it to really know.
Interesting. Yeah. I hate calling like these automated, voice services, whatever. They tell you like, what do you want? And then I say something and they can't get it after like 5 times. It's so frustrating. It's like crazy.
Yeah, they still have room to grow. Systems are pretty amazing.
Yeah, they're improving. Actually, I think maybe recently it's gotten to this place where it's good enough. Like just probably recently. I'm curious how before we get into this full self-driving stuff, how much do you think Tesla's AI and machine learning expertise that they're building up right now, how much is it, do you think, applicable to other areas? Like we just talked about, let's say, audio recognition, right? Recognizing voice or something. And Tesla probably has to rely on other companies like, I don't know, probably Google or someone to, use their voice recognition, et cetera. But like what fields is it something that Tesla can take this knowledge and expertise and actually cross over to, adjacent type of machine learning fields as something to prevent it?
Well, so obviously self-driving cars is a robotics application. And so, taking a lot of the techniques and tools that they developed and moving it to other robots in the real world robot applications like, drones or robots that have to navigate streets or, inside buildings, like that, it could be applicable to that. There's infrastructure. We talked once about Dojo, and you asked the question about like whether I thought like they could go into the business of supplying training computers or neural network training services. And while I think it's certainly possible to do that, that like getting into that business is a complicated thing. On the other hand, doing a technology transfer, like, if Tesla could build Dojo and have it working internally, and then decide that, competing against AWS or Azure, right, from Microsoft, that as a business proposition, like it's too far afield from what they got to do. But you could license the technology, and that could be a good business, right?
Yeah, definitely interesting. All right, let's go for it. We'll go ahead and switch to screen sharing mode here, and you can go ahead and. This is Andre February 2020. Andre Karpathy talking scaled ML. I'll link it in the video description below.
Yeah. So the next set on this is Andre. At one point, he was talking about. So we just went through the section where they were talking about using bird's eye view and how that was giving the vehicle a better sort of situational understanding to allow it to navigate in the world, and how that was a big improvement for them over using the perspective views. So another component of what they need to do is recognize objects in the real world. And there's been this contentious issue of like whether to use LiDAR or not to solve these problems. LiDAR gets used a couple of different ways in vehicles, but one of the topics about LiDAR was the ability to use it to recognize objects in the vicinity of the car. Like this has been the one of the topics that we kind of come back to, like, well, is it worth spending the money on LiDAR to be, 1% more accurate at detecting pedestrians, or, and in safety applications, it kind of sounds like you want to be able to do that. At Scaled ML, Andre talked a little bit about what he called pseudo-lidar. And I think I found the reference where that he originally got that term. I'll show that a little later. But the pseudo-lidar is basically, instead of putting a lidar on my car and measuring, the 3D topology of the environment around the car, what if I ask the camera to guess what a lidar would see? Now, if that's a good enough approximation, like if I can put a camera on a car and I can train the camera to produce the same output as the LiDAR, then I'm getting the LiDAR for free. I have to have the camera anyway. And so he had a talk that basically showed progress against this goal, which he called pseudo-lidar. And that's the image that I have here. So Tesla's approach, at least as Karpathy described it, was they're basically using a self-supervised approach where they use how the camera view evolves over time and how the views from different cameras correlate to train a neural network to learn the depths of all the objects in the frame that it's looking at. And the way that the technique more or less works is the training method. You ask the neural network to guess at the distance to everything in the frame. And then from the geometry of the car, you figure out if this particular car was actually that far away from my car, and from the camera what the angle is, what distance would another camera that can also see the car say about the distance to that car? And you can check those two against one another. So the reason that this is self-supervised is because no humans have to label this data. Basically, if you got cars out in the world driving around, you just record the video, you dump it into the self-supervised training process, and the neural network, assuming the process works, the neural network will learn to recognize distances quite well. And this, he basically is showing in this slide that I have highlighted here what's going on in this situation. So here he's showing three cameras again. The center one is the fisheye view out the front of the car. And then we have the left pillar, which is the left forward and to the left view, and the right forward and to the right view. And then below here is the neural network's prediction of the distances in each one of these frames. So each one of these camera neural networks is just taking this image and it's guessing at the distance of things. So the distance here, it's a heat map where, you've got all these orange and pink pixels, and the brighter they are, the closer it is to the camera. So when you look at this, you can see the outline of this car, and you can see it's put a little box around it. It's identified this vehicle. And then you can see that the building is farther away and that the road in the foreground is closer than the car is. So we can see that this camera is producing a high resolution, good quality depth map just from looking at this image. And likewise, this front image is doing the same thing. In the image, you can't, as a human, it's hard to tell, but there's a car right here that I'm pointing at. And there's a couple of other cars in this view, and then some buildings and the sky, of course. And in this depth map, you can see the car in the foreground really clearly in the depth map. And then the buildings are here, and then these dark sections are where the sky is off in the distance. And once again, for the right camera. And I think, let's see if I can click on this. And you can see it's doing this in real time. So now the other thing that's going on in this frame is this kind of shows how this ties back to the bird's eye view. If you've got these different views projecting out these, estimating the depths of these various objects, then when you go into the bird's eye view, you can now basically say, from the position of the car, like, where are these other vehicles in the frame? And here, this map is giving you centroids for these vehicles and speeds. So we can see that all evolves in time along with this other stuff.
So the right.
So this is just basically the center of these various objects that have been identified.
Oh, okay, got it. So a couple of questions here. So can you explain a little bit more how they're able to get depth through their neural nets? The camera takes, the video, multiple cameras, and it's guessing, right, how far an object is, and then it's comparing itself to the other tricky, cameras. And then also the other question is, are they using, how important is time, like multiple frames over, a few seconds, and how the image changes to determine depth? Do they need that at all, or is it just purely like single frame?
It's super helpful to have. You can probably do it without it, with multiple cameras, but I actually think time is probably more important to them than the multiple cameras is in this instance. So they're trying to teach the car to do the same trick a human can do, right? Like if I show you a picture of a beach scene, just a photograph, it has no depth to it. I can ask you, like, how close is this girl in the foreground? How far is that beach ball? How far is this seagull? And as a human, you can look at that picture and you can make pretty reasonable guesses. You can certainly tell what's pretty close from what's pretty far, and the shape of the ground and stuff like that, right? So how do you teach a neural network to do that, right? Well, the basic way neural networks get taught is you show them a picture and they guess. They give you the way we teach the cat and dog trick. We talked about telling cats from dogs. Showed a picture of a cat, and you say, is this a cat or a dog? And if it says cat, you say, good boy, keep that. And if it says dog, no, that wasn't so good. And it actually gives you a probability when it comes out. It'll say, 90% cat. And in proportion to how wrong that probability is, you feed a signal back through all the neurons that moves the connection weights away from dog, if it's actually a cat, and towards cat, and in the opposite direction. And the amazing thing is you can have all these neurons, and if you just do this technique a bunch of times, back propagation, the more you do it, the more different cats and dogs you show it, and the more times you do that experiment, the neural network, it just learns to recognize dogs from cats. So in this case, what I'm doing is I'm showing the neural network this picture, or lots of pictures like this, and I'm asking it to guess the depth. So then I'm asking it to give me a picture like this output here at the bottom. And what I want to be able to do is say, to what extent is that a good picture or a bad picture, and provide a feedback signal that says that was either good or that was bad. And from the ones that are good and the ones that are bad, it'll gradually settle on a way of predicting this map that works. So the trick is that if you want to do this, like the traditional way of doing this supervised is you have a human being or you have some other machine make a super detailed map, the truth, the ground truth of the image, so that when the neural network makes a prediction, you can say it's right or wrong and to what degree it's right or wrong. You can give it that feedback signal. But say you don't have that, right? I mean, it's not possible to do this trick with LiDAR because it's too low resolution, right? And it's really labor intensive for human beings to go out and measure the distance on all those pixels, right? Because you might need thousands or millions of these images to train this thing. So, but there's, if I'm doing this trick on a bunch of frames in succession, like, and something is approaching the camera or moving away or moving past, we know that the way that the frame changes from one image to the next, it has to follow certain geometric rules. And we can take advantage of those geometric rules to do a trick where we ask the neural network to make a prediction, and then we move forward in time where the scene changes in some consistent way that we understand. And we ask it to make another prediction. And then we look and see if those two predictions make sense, given what we know about the motion of the vehicle through the scene. And if it makes sense, then they both get a good score. And if it makes less sense, they get a bad score, right? And it turns out that this approach actually works for doing this stuff. And that this is self-supervised in this case, where you're using two different takes on something and you're checking them against one another. And that saves having to do all the human labeling, and it saves having to like go out and make these super precise measurements. And I mean, people have been talking about doing this for a really long time, and it's finally starting to work where, we can just have, a multi-camera rig, move around inside an environment, shoot a bunch of video, dump it into a computer, and the computer can train the neural network to do the depth.
Yeah. This sounds pretty revolutionary. Sounds like really cool. Cutting edge.
It's really cool.
Okay. So here's how I understand it. Please, correct me if I'm wrong. So it's basically, the neural net predicts basically what's going to happen. Let's say a few frames or a second later or something. And then it uses those future frames when it happens to basically train to basically say, oh, that was a correct prediction or an incorrect prediction, because you're able to take maybe the speed of the car, the direction of the car, different geometric, attributes to determine that. And so it's basically, it's self-supervised in the sense that you don't need any human labeling because the labeling is already incorporated in the frames, the feature frames, right? It's just because you're saying, predict me what's going to happen in the feature frames, and then you take the feature frames and you just correct.
And use that, and that's your check. Was it good or bad? And
and
then the feedback signal. Yeah.
And then you're training your neural nets that way, but it seems like an incredibly crazy efficient way to do so. I mean,
so if you do supervised learning, which is where humans have to label everything, that every single test sample is super expensive because some human being has to like sit there with a magic marker and mark this puppy up, and it could take an hour to mark up one frame. And if you need millions of those, that's a lot of labor, right? Unsupervised stuff, kind of the holy grail, is where you just expose the system to bunches of data, and then it learns to predict data from other data. And self-supervised is kind of this intermediate ground. It has certain constraints, but both self-supervised and unsupervised don't require humans to label. So if you can get a lot of data and you don't need humans to label it, then you're kind of, then it's just about, how much the computer time costs. You can do it.
What's the difference between unsupervised and self-supervised?
So unsupervised learns without any constraints on the data. It learns to predict the data. And self-supervised predicts some of the data from other bits of the data. So for instance, language models, the way that language models get trained, like GPT-3 right now, is you take a sentence, you give it a sentence, and then you take away some of the words, typically 5 to 15% of the words, and you ask it to predict the words you took away. So that's self-supervised because I'm asking it to predict parts of the data that it doesn't have, but it has the other data to work from. It's not predicting something, whole out of whole cloth. It's, it's what I'm doing is I'm abbreviating. So in a sense, this is self-supervised because say I've got that video stream, right? And I'm asking it to predict parts of the video stream it doesn't have from parts it does have. So then technically that's self-supervised. And the distinction is that, I mean, it's kind of a technical distinction from, self-supervised is pretty good stuff. Unsupervised is kind of the holy grail because you can learn anything from just raw inputs with unsupervised. Incidentally, we talked about a single camera view moving through, but there's actually two tricks that they can do, which is one of them is, say you got two cameras with overlapping views, right? And you have one camera predict the part of the other camera's field of view that the other camera can see. So that's the other thing they can do. So without moving, you can have like the fisheye overlaps with both of the pillar cameras that face forward. So if you have the pillar predict what the fisheye is seeing, and the fisheye predict what both pillars are seeing and that kind of stuff, that's the other way to do this trick of essentially have one camera predict what the other camera can do. And if the predictions for both networks make sense, then they both get a thumbs up. And if they don't, then it doesn't. But the temporal one, I feel like in this situation is probably much more powerful because you've got a lot more data. A given camera, you get 30 frames a second. You can drive for hours, right? You can collect all the data that you want.
Yeah. I mean, it seems like, you have the unlimited amount of data basically, because it's self-supervised. So
they've got that fleet out there. It seems like a million cars driving around. It's if they can make self-supervised work, and it seems like they can, because that's in this talk. That's Andre says this is how they're doing this, and you can look at the results. At least, I mean, this is maybe he cherry picked these, right? But it looks pretty good. It looks like they can do it. So so there's a very interesting thing that you get from this, which is important. And I think I've pulled up this. I don't know if you can see this paper.
Yes, I can.
But so this is a paper from mid 2019, and you can see they're using this terminology pseudo-lidar in here. And so in this, what they did was they pointed out in this that if you're trying to recognize objects in the real world, if you have a LiDAR and you have a camera, you get a certain accuracy. If you just have a camera and you're using state-of-the-art systems, you get a different accuracy, which is much inferior to the accuracy for recognizing objects that they were getting at this point using the camera combined with the LiDAR. So they asked the question, what if I ask the camera not just to identify objects, but I ask it to predict what the LiDAR would think of this scene? In other words, I do pseudo-lidar, right? Well, in order to predict what the LiDAR is going to see, the camera has to get the idea that the world has depth, right? You're asking it straight away, what's the depth? And it has to figure that out. And it turns out that once it's figured out depth, all of a sudden its ability to recognize objects gets dramatically better, because one thing about objects is their depth is different from the surroundings, right? I mean, that's a fundamental thing. You can ask a human being and they know that that's true. It's just a characteristic of objects that they're isolated things in space. And so one thing that delineates them from the environment is that when you look at them, their depth is different. So indirectly, they ask the network to predict depth. And what they find, and I've got this result down here, is that all of a sudden its ability to recognize objects gets a lot better. So this is kind of one of the slides from their thing where they show, so here's the camera combined with LiDAR, and this is, let's see, so the ground truth is red. So red is what's really there. That's what they want the network to predict. And green is what's coming out of the neural network that's trained. So this is what it looks like from the side, and this is what it looks like from the side. So you can see that the red boxes and the green boxes, they overlap really well for all these cars. And these are ones that are close to the camera, and these are farther away. So we go to this. This is the pseudo-lidar with stereo. And we can see the pseudo-lidar, it's also doing a pretty good job. The red boxes and the green box. You have the ones way out here at the end where you're looking straight at the end of the car, they get a little bit of error, but this is doing pretty good. But this is the camera by itself. If you don't ask the camera to learn about depth, you can see the errors on these. Even the close vehicles are pretty large. It does great on this vehicle. It's not so good on this one. These are kind of off, and it doesn't even detect these two. Right. So basically, by asking the neural network to predict depth, Even if the thing I really care about is recognizing the cars, it turns out that once I challenge a neural network to learn the depth in the scene, all of a sudden its object recognition gets dramatically better. And I think this is a big part of why we see Tesla doing this in this scene. They don't necessarily need all of this depth data, but what they need is, by challenging the neural network to learn the depth, they're going to make the object recognition a lot better. And they can learn the depth from self-supervised data. So once they get the technique worked out, they can just have the neural networks learn depth. And once the neural networks learn depth, their object recognition just gets a lot better. So this is a super powerful technique for significantly improving the accuracy of the car's ability to recognize objects in the world.
Yeah. I mean, do you think also as the neural nets recognize depth, also the bird's eye view will get more accurate as well?
Yeah.
Yeah.
Absolutely.
Yeah, I mean
that's going to be a component of it, and it's sort of illustrating it in this frame. Actually, you can, because in this slide, Karpathy is talking about how essentially they're using depth to predict this as a component feeding into this bird's eye view thing. So if we go back to that, maybe I can find it quickly. This slide so this is the slide that shows the structure of that we were talking about before, that they're using for the bird's eye view approach, where, you got 5 cameras, you have these 5 backbone nets, then you fuse them in space, you fuse them in time, and then you ask for this rotation. The depth net, when they train these things, they train depth in the self-supervised way into these core networks. And so what happens is, because these networks understand depth, the output component that they produce also has all that depth information in it. So by the time they get down to the BevNet, they're able to take advantage of that. And of course, all the object recognition gets a lot better because of that characteristic objects have, where objects are not space. Space has a lot of depth to it, and the objects have less. And so you can use that to recognize objects.
Interesting. Definitely. Do you have any more comments on the skill demo video?
No, that was the last for this.
I'm wondering if you could dive into a bit more in terms of the strengths and weaknesses of a LiDAR approach versus a vision as a approach. So it seems like with this pseudo-lidar approach, if you train the neural nets to, measure depth, then you get, it seems like almost all the benefits of LiDAR, in the sense of you're able to map out your surroundings. I mean, are there any limitations to kind of more of a vision-based approach that you won't get without having LiDAR?
So in this case, it's going to come down to, like, how good is that depth prediction? If the depth prediction is arbitrarily close to the LiDAR prediction, then you get nothing from adding LiDAR to the system. It's just redundant. So when your object, if you're using LiDAR to enhance your object, LiDAR, it doesn't mainly get used for recognizing objects in vehicles that use LiDAR for driving. It does other things too, but if we're just talking about object recognition, if your depth prediction is good enough, then the LiDAR doesn't add anything. So the question is, given a certain amount of resources, like if you decide to have LiDAR versus not have LiDAR, it has implications for, like, how much the car costs, and how complicated it is, and how easily it breaks, and how you do your training. You have to devote resources to it, right? I mean, you've got this resource budget, and some of it is people, and some of it is money, and some of it is the cost of the vehicles out there. And so if you want to put this sensor, and not just LiDAR, there are lots of other sensor modalities. Like there's multispectral cameras. Like once upon a time, I thought multispectral cameras were going to be the way to go, or thermal infrared. Thermal infrared is this great dimension, right? It's way cheaper than LiDAR is, and it gives you this other alternate thing. And then there's radar. Radar also is another thing that you can fuse. Every one of these sensor modalities brings something to the system as a whole, and every one of them has a cost. So you have to ask the question, what is that going to cost me? What is it going to cost my product? What is it going to cost my development? And what am I going to get for it? And it's pretty clear that Tesla's take on this is that when vision is mature, LiDAR won't get you anything. And I think Elon compared them to appendices, right? You're gonna have all these expensive LiDARs on your car, and you're gonna be getting nothing for them once the neural networks are mature. And personally, I believe that that's true. So I think that's the right trade-off in the short run. And until the vision systems are that good, then maybe there's some merit in having a LiDAR on your system. Is it enough merit to cover the cost of that system? That's a complicated trade-off, because you have to predict the likelihood of like how close the gap closes between having LiDAR versus not LiDAR. And once again, this is just for object detection that we're talking about. Like how close is that gap eventually going to get, and how long is it going to take to close that gap? And Tesla has bet that gap is going to close pretty quickly, and the other players are basically betting that gap isn't going to close for a really long time.
I mean, with LiDAR, besides depth, right, and object detection, and also I guess LiDAR can help you find your exact position perhaps on the map. So in conjunction with HD maps, you could find out exactly, where you are in that picture. Is there anything else that LiDAR brings to the picture?
Well, I mean, I haven't looked inside like Waymo's code, but what I hear is that localization is the main reason that you see the big play, like Waymo and Cruise, using it primarily for localization. So if they do this really detailed map of an environment, you can basically take a LiDAR return signal and cross-correlate it with your map, and you can figure out where your vehicle is in a very straightforward way. You can figure out where your vehicle is to whatever the resolution of the map is. So if your map resolution is, a centimeter or 3 centimeters, you know exactly where your car is. And so if you pre-map the parts of the roads that are all the physical things that you don't want to bump into, right? That technique absolutely guarantees that you're not going to hit a curb. Not going to hit a curb, not going to hit a wall, not going to hit a sign, as long as your map is accurate, right? And so that requires you to have a really high quality map if you're going to use that. And it requires that the world not change in ways that break your map very quickly. So like every time, construction breaks your map. I mean, various things can break your map. And it requires you to like go in and build detailed maps and maintain them. But it solves a really useful problem, which is you can guarantee that you're not going to hit any of the static objects in the world if you do that trick. And at one point that was super useful. Of course, not hitting cyclists is a much bigger challenge than not hitting curbs. It's also a much more meaningful one. So in a world where you have to be good enough to not hit the cyclists, you got to wonder, like, what's the utility in guaranteeing that you won't hit the curbs?
Mm-hmm. Got it. With LiDAR, it's my understanding that the images are not as sharp, right, as a camera. So, I mean, how sharp are these LiDAR images? Are you able to actually read, signs on the road with LiDAR, or is it just too blurry?
So LiDAR LiDAR can give you a return color signal, but that's not why people use it. It doesn't give you a return color, it gives you a return intensity. You wouldn't be able, LiDAR is not, okay. Better LiDARs have better resolution. And good LiDARs cost $100,000. Google claims that they've got a pretty good LiDAR that they spend $8,000 on or something. They develop it internally. That LiDAR won't be able to read a street sign at any distance. It doesn't have nearly the resolution to be able to do that, even so. It just gives you a depth for each one of the pixels that you point out, and you get a pretty coarse map. It's fine enough that you're going to get a couple of dots on a pedestrian if they're within, 50 feet of the car or something. But you might not, you won't be able to see a wire, and you might not be able to see a skinny pole if it's more than a small distance away from the vehicle. And there are things that can give you problems, like glass reflects LiDAR super effectively. So, but glass does this for passive optical too. But a LiDAR, if you're driving by a big glass building, it'll see a bunch of cars on the other side of that glass wall, right? Because it reflects really effectively. Mm-hmm. And when you see the rear of a vehicle ahead of you, the reflection will be the sky. so you won't get any distance on, on that portion of the thing. LiDAR's got some limitations. It's very popular because in the short run, it makes your software development easier.
I mean, it seems if, Tesla's approach with vision and passive optical can actually, I mean, if they're doing, self-supervised learning with, depth, I mean, it just seems like this could radically improve very fast. And it seems like it's very likely or possible that they could achieve, a lot of what LiDAR can do in terms of depth and mapping with just passive optical. And then you add on top of that, Tesla's cameras can read signs and read markings and navigate like a human can navigate. I mean, in the scaled ML talk, there's that section where Andrej Karpathy noted the stop sign said stop sign. I think it was except right turn only or something, right?
Except right turn.
Yeah. So
we have the world's biggest collection of stop except right turn signs in.
Yeah. So I mean, Tesla,
he showed like 50 of them.
Exactly.
Right?
Yeah. I mean, you stop except if you're doing a right turn. So right turn, you just keep on going, right? So if you're taking a left turn, then you stop. How is LiDAR going to navigate stuff like that? They just can't.
So LiDAR's a supplement to vision. It's not a substitute for vision, right? An argument I think Elon got asked some time back about vision versus LiDAR or whatnot, and he gave a response which I really like because it's always been my response, which is your vision has to be really, really good. Our whole driving system, like all the obstacles, the road rules and everything, they're designed for people to drive with their eyes, right? Our road system is designed for vision, and you have to have good vision to drive. You just have to. You can't have poor vision and feel like you're going to do well. You're going to do reasonably well. The thing is, if you have good vision, then LiDAR doesn't add anything, right? LiDAR it gives you something to the extent that your vision isn't very good. But where is that line where your vision is good enough to drive a car if you have LiDAR, but it's not good enough to drive a car if you don't have LiDAR, right? There's that little spot. And people who are putting LiDAR on cars, they're gambling, they're betting that that's where the world is going to end up for a really long time, that we're going to be in that gap where LiDAR adds a lot of value. But vision is good enough to drive as long as you have LiDAR. You have to have good vision, and you have to have really good vision to drive in the world.
I mean, if you're dependent on LiDAR, though, will you be dependent on HD maps as well? So you can only drive in places with HD maps, or will, let's say, vision plus LiDAR, will that be used, you think, to attempt to drive on non-HD mapped areas as well?
So I mentioned that LiDAR is doing two things for most of the people who are using it. When Cruise uses LiDAR, they use it for localization. And then it's very likely that they're also using it for object detection. They're using it to supplement the cameras to enhance their ability to recognize objects in a scene. If you want to do the localization function, you have to have the HD maps. You could have LiDAR and not do localization and only use it for the object to reinforce your object recognition accuracy. But you would be using a pretty expensive LiDAR for a subset of the things you can do with it if you did that, which I think is one reason why most people who commit to LiDAR, they also commit to HD maps and localization.
When do you think the folks using LiDAR, let's say Waymo or Cruise and some others, when do you think they will reach a point where they're like, our approach is not working out as well as we thought, or let's say they recognize maybe Tesla's approach is better. I mean, it seems like with LiDAR in some approaches, it could be better. Like, for example, if you have a set route, in a city that never changes, it's a bus route or something, right? And you're just always doing the same thing. It seems like, hey, maybe that's, could be decent for LiDAR. But like, do you think there'll come a time when everyone just basically acknowledges that vision, passive optical is the way to go without LiDAR? And how long do you think that would take?
Vision is definitely going to get to a point where LiDAR is not going to add enough value to justify its cost. So I also worked in nonlinear optics for a long time. I used to design transceivers, and I worked at a company. We had the biggest gallium arsenide fab, and we made all these infi lasers and stuff. And so I got to watch a lot of nonlinear optics development over the years. And it's not super easy. And I'm not really expecting lidars to get cheap as fast as lidar proponents think it's going to. Now, if you think lidar is going to get really good and really cheap really fast, then that could change the equation. But like my guess is that that's not going to happen very quickly. As long as it's not super cheap and super good, then it has to be supplying a lot of benefit on top of your vision in order to justify putting it in vehicles. And I don't think it's going to justify that, at some point. Which I think is, like, if I'm going to guess, I'm going to say it's pretty close. I'd be surprised personally if 10 years from now, people were developing new systems and that were cost sensitive and putting lidar in them. If the system, if you have the resources to do the software development to make the vision good, and your end system is cost sensitive, then I think you won't be putting lidar in. But people who they build a piece of factory automation. They're not going to get a lot of data, and it's already $100,000 robot. And then maybe they'll put a $10,000 lidar on it, and it will totally make sense because you'll get the benefit out of that. It'll make sense from a cost standpoint, but I don't think it'll make sense in cars relatively soon. But I don't expect the people who are doing that to say, "Oh yeah, we were wrong. We're going to take the lidars off the car." Like, you're not going to see that happen.
Yeah. This is kind of off the topic question here, but so there's a company called Matterport, I think, and they do 3D kind of layouts for real estate. So people, they buy the Matterport camera. I think it's a LiDAR camera, and then you basically walk through the house, and then it'll come up with a 3D kind of layout of the house. People are spending several $1,000s on this camera, et cetera. Is it possible, do you think, or when do you think it would be possible for people to be able to come up with a layout purely using passive optical or using cameras? Like, do you think you need LiDAR to do that?
This phone's got LiDAR on it, and I think you can probably do it with this one now. Really? Huh. I don't think I think that the thing that's preventing you from doing that with an iPhone 12 or an iPad Pro, a recent iPad Pro, is probably software more than it's tech. Can you do it eventually doing it passive optic? And I think you can already do it passive optical with a neural network. Like, people have demonstrated doing this kind of stuff, but the sample efficiency is better if you have LiDAR. That is, the amount of time you have to spend walking around the room before you get a really good model is lower if you have LiDAR than if you use passive optical right now. And that, what'll happen is that gap will just get smaller and smaller, and eventually it'll be small enough that the LiDAR won't matter. And that's, that's not that far away either, inside 5 years.
So you think inside 5 years, people will just, I guess with your iPhone camera, can you, what kind of LiDAR is on the iPhone 12?
It's a pretty coarse LiDAR, but I mean, there are applications for doing what you're talking about with this already. Like, I haven't spent a lot of time playing with them. I've seen, you can, if you go on YouTube and search for, people doing depth maps with the iPhone 12, you can find examples of people using apps to do that kind of stuff. Matterport's, I haven't used their system either. It's weirdly, I happen to know the guy that started that company. But I only followed it in the early days, so I don't know what the status of their product is right now. But it is a pretty mature product, and it is tailored to that business. I think for professional real estate developers, where that's a big, where the money's not that important to them, that they'll keep using those systems because they're tailored to that application. But I think, for somebody who just wants to make a model of their own house, I think you can already do it with an iPhone right now if you put the time into it and buy the right software.
Awesome. This is fantastic. I'm learning a ton. Is there anything else you wanted to bring up on the Scaled ML talk before we wrap up? Okay. Sounds good. Wanted to extend, my thanks and gratitude for sharing being generous with your time. It's helping me a ton, and I'm sure others as well. And just to kind of get, a deeper look at some of the stuff going on, because sometimes I think it could be over the head of a lot of people, but this is actually quite amazing stuff that's happening before our eyes. We're seeing this massive, innovation
I really would
and
like
change.
it to be more accessible to people.
Yeah.
Or it's, you know, I've been in this space for a really long time, and the time that we're living in right now for this field is just, it's just nuts. It's just crazy. Like I mentioned the Wright brothers example before, that when human flight was happening, when people who were living through that era where, a couple of years ago, they thought it was impossible and it was this ancient dream from, the Greeks had dreamed of flying and that kind of stuff. And all of a sudden it's possible. And then all the possibilities just exploded. Flight went from, it was 25 years from the Wright brothers to Charles Lindbergh, right? 25 years, right? Until like a guy got in a plane and flew across the Atlantic Ocean. Imagine how impossible that seemed to somebody just before the Wright brothers. And 25 years later, Chuck Yeager's getting in a rocket plane and he's going, 15,000, I don't know, some crazy speed, right? In no time at all, flight it completely changed. It went from this impossible thing to like every day, and now it's completely changed the fabric of the world that we live in. The fact that you can get in an airplane and fly someplace. Deep learning is going to be a much, much bigger deal than that. And when we look back on this era, 25 or 50 years from now, the world is going to change more than flight changed the world. And it does somehow seem kind of invisible, despite this. That AlphaGo documentary that they made about that, I feel like is a pretty good way of capturing a little instant, right? The AlphaGo documentary, it just talks about like basically this 6 or 9 month window of time when they were working on this. So it's just the tiniest little slice of what's going on. And you take what happened in that documentary and now multiply it by 20, and that's what happened since this technology started. And then multiply it by 100 or 1,000, and that's what we're going to see over the next 20, 30, 50 years.
Yeah, it's fascinating. It's also fascinating how it requires like a convergence of various things together. Like you had, the development, the explosion of neural nets, but then you also have initially the GPUs, but then now you have more specialized chips and software. You have the training element. You have new techniques and approaches, to analyze and so all of these things are converging at the same time to allow for something like, a Tesla full self-driving thing to come into fruition. But it just is like technology is allowing, more and more kind of applications, and it just seems that the pace is so fast in terms of the innovation, especially with neural nets, because especially when you get into this like self-supervised or unsupervised, like this learning, like that seems to be like also a completely different, trajectory if you're able to get there.
So there's another way of thinking about this, which is also kind of interesting. Not that either one is true. They're both just interesting ways of looking at it. So there were two reasons that I got really interested in I was actually working on graph node networks, and neural networks are a subset of that. I was doing that for some years before ImageNet. And one of the things that got me really interested in it was I looked at Moore's. Unlike a lot of people, my basic belief is that Moore's law is going to keep going. The strict interpretation of Moore's law, where they're just talking about the number of transistors or whatnot. Not that one, but the one where the amount of computation that you get per dollar is just going to keep going up this crazy curve for a really, really long time. And I was asking myself, what are we going to do with all that? Like how good can your video game be? Or like, how fast do you need your spreadsheet to load? It's clear that at some point we get these paradigm changes. And the thing that seemed obvious to me at that point was, well, it's going to be machine learning, because that's a bottomless pit. Like you can just throw data centers into that all day long and it can just eat them up. Like you can get value out of that. So that was one thing that was interesting. But there was another thing that was really interesting to me about machine learning like 20 years ago. And that was, it seemed like the thing that neural networks are trying to solve was the missing ingredient for a lot of things, right? Like there were a whole lot of really interesting things that we could do in the world And the only thing we don't have is the ability to do that trick that animal brains can do, that human brains can do, where they learn from data. They learn really complicated stuff from data. That if you had that, there were all these other, things that, we've got all these dumb machines, and all of a sudden the machines can be smart. And a smart machine is orders of magnitude more useful than a dumb machine is. A car is useful for hauling things around, right? But a car that can drive itself, it's a whole different level of useful, right? And so frequently when I think about this, I think about, we got the missing ingredient. Now there's all these puzzles in the world that have that one hole, and we're going to go around, we're going to plug that piece into those, and now we're going to have the big picture on so many things that have been sitting with that empty puzzle piece for 20 years or 50 years or something.
Yeah, definitely. Yeah, I feel like, we could go on for a very long time. I have so many actually other questions and topics I want to toss your way. So what we'll do is we'll try to push this for another week. Actually, I wanted to ask you about Project Vacation. I think that's something that came up in Andre Karpathy's talk. What your take is on that?
Operation Vacation.
Yeah, Operation Vacation. What that is with Tesla FSD. And then I also wanted to ask you about competition and your thoughts on kind of how the next 5 or 10 years might shape up or shape out. And, can people catch up? To what extent can they catch up? Just kind of go through some different scenarios with you. And then I also wanted to this will be the following week, but also take a bunch of viewer questions, because I know people have a ton of questions they want to ask and stuff as well. But I felt like it'd be good to take a couple weeks just to lay it down, the foundations of understanding, and then we'll go into some other questions. But overall, awesome time. I feel like it's a personal, like a study class, like just learning about all this stuff. And then it's not just I benefit, but everyone in the world who has just an internet connection can just actually learn this stuff too. And so it's a huge amount of benefit I think everyone receives. But thanks for sharing your knowledge and being generous about your time.
Yeah, I'm happy to be here.
Okay, cool. Thanks, James. We'll talk later.